Today, I'm just going to give a brief introduction to inquiry question one, which is probably the least important overall. It's a lot of just context to learn for the rest of the module. Um, and I might be underselling it a bit, but in terms of questions, it's where you get the least amount of questions from in exams. That's not to say that it's not important. It's just how it is. Inquiry question two and inquiry question three have a way more heavy number of questions in exams, just from the nature of the inquiry question. So, um, right now, you've assumed to have been watching the introduction video and you've got like a brief understanding of what's going on with acids and bases. At the start of the booklet, I kind of give a different introduction about like why do we spend a whole topic on essentially hydrogen, like Pete. Acids and bases are all about hydrogen. And here's a bit more to it. None of this is needing to be regurgitated in any exam or anything, but at uni I learned about this Grottis mechanism. I'm probably butchering that name. But it talks about like hydrogen can basically just bounce around off every water molecule, making that H3O plus. And because it can bounce and it can kind of be transferred very quickly from one side of a solution to the other. If it was this H plus by itself, which it isn't, so just a single proton, and it didn't attach to water, it would have to move through water to get to the other side and react. Okay, so by this mechanism, hydrogen can move around really fast. Okay? And then I talk about how hydrogen's the smallest element, and so it's just basically a single proton. It's incredibly small. It's not an atom. It doesn't have any electrons, so its radius is incredibly small. You won't get any other element to be just its nucleus because just by the nature of it, like helium will always have its atoms attached unless it's doing nuclear decay, which is very rare. And we're not really dealing with things that are decaying. We're dealing with elements, and so out of all the stable elements, this was the only one that you'll find as just a nucleon, a proton or a neutron. And so in the quick summary, this all talks about how that extra hydrogen, if you have H3O plus, can react with your eyes, your throat, your mouth, your cells, and change its shape and cause it to spill its contents out. And so this is just a bit more of a summary of that. You go, well, the hydrogen's able to move fast. It's incredibly small. It's reactive because it's just a single proton. It's prevalent, hydrogen's everywhere, it's in water. And so you get the whole topic on itself, and there's a need to monitor hydrogen. So this whole topic is essentially about hydrogen and how essentially we need to manage it and be aware of it, and how it can change every living thing, protein, cells, compounds, etc. So for the first inquiry question, the first part of it says investigate the correct IUPAC name. So that stands for the International Union of Pure and Applied Chemistry. Nomenclature, which I never say properly, but basically the naming system in Latin for the properties of common inorganic acids and bases. So know how to name things like sulfuric acid, carbonic acid, and that for common ones. And there's a list down below. Then it says, conduct investigations to demonstrate the preparation and use of indicators as illustrations of that. So we're going to say this first one is basically saying, well, how do we measure how much hydrogen is in a solution? And one of those answers is indicators, literally just chemicals we put in there, and there's a certain color, and that dictates what kind of pH range we're in. Well, that tells us what kind of pH range we're in. We now use pH probes, which we'll get into a bit more. pH probes actually measure conductivity, the conductivity of the hydronium ion in particular. In part C, it says, be familiar with these things that you've been trying to get familiar with since year 10. So you need to know that all acids and bases make salt plus water, acids plus carbonate, and acid plus metal. And in a lot of these ones, in the first two, the real reaction that's happening is a neutralization reaction. Okay, and This one might be a bit hard. You might need to refer back to the old video, but essentially it's just the hydronium ion bumping into the hydroxide ion, bumping into water. Okay? Producing two waters, sorry. And then it says, investigate applications of neutralization reactions in everyday life and industrial process. So this is a neutralization reaction. We're heading a solution that is too high in acid, or too high in hydrogen, or too low in hydrogen, and we're neutralizing it back to the right ratio. And where do we do that in life? And then there's another one that says, conducted practical investigation to measure how much heat is given off from neutralization. And we're going to learn that this process is exothermic and almost always negative 57 kilojoules per mole if done correctly. Right? And then you learn a bit more on top of that, okay? But that's a general rule that this process is exothermic. We know that if you ever do an acid-base reaction and you fill the test tube afterwards, it's always hot. You can actually measure out how much energy comes off by measuring temperature change and then using those formulas that you can kind of remember, Q equals MCAT, and then changing H equals negative Q on N. Okay. And then this last one, to cap off inquiry question 1, says explore the changes in definitions and models of an acid and base over time and explain the limitations of each model. And then it says included but not limited to these two ones, so Arrhenius theory and Bronsted and Lowry theory. And the quick summary on that is there was a guy called Davy. Oh, sorry, I'll get back to that. The first one is a guy called Lavoisier. And he's like the guy that started all the naming systems, and he was playing around with a bunch of acids, and he was actually using electricity to split them up into their individual parts. So for instance, if you had phosphoric acid, he was trying to split phosphoric acid up and see what individual elements it was made of. And he kept getting oxygen gas produced, even though he knew there was a lot of hydrogen produced. He thought oxygen was the main element. And so he goes, oxygen must be the common element in all acids. And they knew what acids were. Acids were the things that when you put it on your mouth were sour. So it comes from the word acere equals sour, right? So acids are things that react with metals to produce hydrogen gas. You could classify them quite easily in the day if they're an acid or not. And he found the common element was oxygen. Okay, so he goes, it was oxygen. And that was later proven wrong, right? But the funny thing about that is oxygen indirectly means acid maker. And so it's kind of incorrectly named on the periodic table. Then there's another guy, Davy, who basically said, no, it's hydrogen in all is the common element. And he was right. Okay. And he has no theory. All they've done is identify the common element. And so they're not really a theory of acids and bases yet. They're just like the prelude to the story. And then come along a guy called Arrhenius. And he actually did his PhD and basically said, he was trying to explain why water, like pure water, is basically not conductive, does not conduct. But like you chuck any salt or acid in it and it does conduct, right? And we know now that that's because, you know, if you're measuring the conductivity of a strong acid, say like hydrochloric acid, the most familiar one, from the last one, you should realize that now it's splits apart into its ions, and these things conduct. They're able to carry some electrical energy. And it's actually this. So it's not the H2O that's conductive, it's the ions that are conductive, the things that have charge. And he doesn't know about this hydronium ion, he doesn't know about chlorines. The word ion hadn't even been invented yet. Okay? And so he's starting to introduce the idea of ions and charge. to explain why salts and acids have conductivity. And his paper passes, his PhD passes, but I guess the lowest score, like basically passes with 50%. And then it later, after people like kind of evaluate the depth of the idea, so later it gets a Nobel Prize. And his theory is pretty easy. Right? Easy now. Everything's easy in hindsight. His theory is acid equals something that dissolves in water to give H plus, right? Base dissolves in water to give OH minus. And the reason, a big part of why he wasn't accepted is H plus. Most people said you can't have this reactive proton just moving around everywhere. So if I go back up into this, they're basically saying that guy is too reactive to be floating around in solution by himself. And so obviously he didn't know about this mechanism and he didn't know about H3O plus. And he essentially, it makes a lot of sense, but everyone hated this. And so how do you change it to, how do you got to pass that idea and went H3O plus, you know, he might have been more accepted. And he was also kind of stuck with this water example. Everything has to happen in water. Now, Arrhenius was explaining a lot of chemical reactions, a lot of acid-base reactions, but he wasn't explaining them all. Then there's this ammonia dilemma. Basically, someone soaks a cotton bud of ammonia at one end of a glass tube. They've got some universal indicator here, and then or an indicator, a chemical, and then they pour in HCl gas form. It's called hydrogen chloride, not hydrochloric acid in aqueous form. This is hydrogen chloride. And these gases diffuse towards the middle of this glass tube, and they react to form ammonium chloride. And ammonium chloride, you might remember, is a weak acid, and this is an example of a color change that indicates that there was an acid-base reaction. And so it was clear that water doesn't necessarily have to be present. And so the next model that comes into it is this Bronsted and Lowry theory. And they were kind of working on the same idea independently from each other. And they were like months, within the same month or a couple of months, they published basically the same work. So they weren't working together, they got pushed together. And their idea is a more general one, is a hydrogen donator and a base is a hydrogen acceptor. And these models are very good. This one can almost explain all of them. This one can only explain acid-base reactions in water, and it's a bit limited by the fact that it has H plus instead of H3O plus. And so this guy's pretty good as a starting tool. This guy's Bronsted Lowry is the most generic one and the one that probably everyone leans on. Technically, there's one after called Lewis acid-base reactions. Lewis, when you go to uni, is a heavyweight in the chemistry world. And he actually said that you don't need hydrogen for an acid-base reactions, but I won't go into that in this video. But essentially, there's one after this that more generalizes it, talking about nucleophiles and electrophiles and that kind of stuff. And so, quick summary is Lavoisier said there was oxygen was the most common element. He was wrong, and hilariously wrong, because oxygen means acid maker. Davey said, no, it's actually hydrogen. Arrhenius says it's an acid, it's something that dissolves in water to give H+. A base is something that dissolves in water to give OH-. It's got its limitations. You can look into it a bit more. There's like specific examples that they can't explain. So for instance, I can't think of one off the top of my head, so I'm just going to skip over it. But there's some ones that don't dissolve to give OH- straight away, or so they don't have OH-. So something like ammonia doesn't dissolve to give OH-. It reacts to give OH-, and only a little bit. So because ammonia is a weak base, when it bumps into water, it only produces a little bit of hydroxide, but it also gives a bit of the ammonium ion. And so you might be able to detect this back in the day, like the conductivity might go up a little bit in the solution, and you might be able to see a color change if you're using a chemical. But essentially, Arrhenius would struggle to classify this as a base. That's because it doesn't contain the hydroxide in the first place. So he'd be like, sodium hydroxide, boom, that's a base. Conductivity went up a lot because it's a strong acid, a strong base. So it fully dissociates into sodium and hydroxide. And these guys would have, because all of them are split apart, they'd have high conductivity. And then you got this is the ammonium problem that I talked about, where you get NH3 plus hydrogen chloride gas, and that makes ammonium chloride. Because that didn't happen in water and happened in gas form, right? Happened in gas form, then Arrhenius's model has a limitation, and Bronsted-Lowry's general one is pretty good. It covers pretty much all acid-base reactions besides very specific ones. In fact, I've got a nice summary table down here, which you can pause the video and try to explain a bit more.